Hi, so today we'll be doing experiment 4, metallurgy. You're going to bring your worksheet. This is going to be a long ride. So we're going to start off at the grinder. So we'll be having this steel sample from your year 1. So similarly, we have to turn on the power. Then we'll first start out with the 400. 400 means it's coarse. The smaller number it is, so it's coarser. Then 600 is finer. So for this, you need to have the tap fully on. Then we'll hold the sample against it. Just hold it firmly for about 5 minutes. Yeah. So in any case, if the test piece drops, remember to switch off the water, off the power, wait for it to finish, then pick it up. So when you're done, wash it off. And you may continue. So after grinding for about 5 minutes of this, we'll move on to the next grinder, so 600. Similarly, let the tap run. Turn on the power. Then grind again. So you do this both for about 5 minutes, but for this video we'll only be doing it short, just as an example. So once you're done, switch off the water, turn it off, wash off the residue, and then we're ready to move on to the next part. Okay, welcome back. So once you're done with the grinding, we'll move on to the next part, which is polishing. So we'll start off with pre-polishing at 5 microns. So the thing that we'll be using to help with that will be alumina slurry. It's also a solution. So remember to shake it first, then open up, dip about 1 to 2. So I think that's it, yeah. So then turn on the water, but for the water wise, you only want it dripping, because you want to keep as much of the solution as possible. Oh, yeah. Okay, so turn on. So the same thing, hold it as long as possible for about 5 minutes. Once you're done, let's say 5 minutes later, we can stop, move on to final polishing. Same thing, this time we'll be using a different alumina slurry. This time is 1 micron. So the final polishing. So shake it, 1 to 2 drops. Then turn on the tap again. Okay, you need 1 dripping. So turn on again, same thing, hold it. Then you should have a shiny exterior towards the end. So something like this. Okay, so from here on out, we'll move on to etching. Remember to wash it after you're done. Okay, welcome back. So the next part we're doing will be etching. So we'll be using this machine specifically. This is a fumes head, a ductless fumes hood. So basically, we'll be using something poisonous called nitrile acid, but actually we're using a solution. So essentially, nitrile acid will release toxic fumes that we as humans don't want to inhale or have it in contact with us, with our skin. So we have to turn on this machine. So the switch will be at the cupboard below. Once you turn it on, the machine will be warming up. It'll take about 3 minutes. Yeah. So after 3 minutes, I'll get back to you. Okay, welcome back. So now we'll be doing the etching. Our most important tool is our safety tongs. This will be one of the precautionary measures. So first we'll move on to the nitrile acid. We have to use the tong itself, hold it up, rub it, and immediately go to the alcohol. Leave it there, hold it for about 10 seconds. So once we're done holding for about 10 seconds, we take it out. Immediately we'll move on to the sink. Once we're on the sink, we'll use the ethanol and wash it with it. So once you're done the ethanol, you can just wash it off. And that should be it with your etching. So if you want to, so your final test piece should have some grain on around its sides. As you can see, some parts are reflective, some parts isn't. So yeah, this is basically what etching does. But this one you're done in year 1. So from here, we're gonna bring the test piece to the microscope room. So we're gonna check for the grain size, essentially your metallurgy. So yeah, that's it. Hi, so welcome back. Right now we'll be using the microscope to check on whatever we did with the etching. So the switches wise, we have 2 here, 2 more here, turn on, then another one just behind the monitor. So then from here, you have to turn on this switch here. This will help to connect the lighting with the microscope. Then behind the microscope itself, we have to turn on something as well, which will also connect to the monitor itself and the PC. So in this case, you put the etching right here, and during the experiment itself, if we have time, you guys will be able to check exactly what you guys have done. Yeah. But in this case, we have already prepared some samples for you guys to check on, and which will be tested. Sorry, not tested. Which will be specifically used for your questions on your experiment paper, on your experiment worksheet. Yeah. So from here on out, let's move on. We'll move on to the PC itself. So first things first, we'll be focusing on 2 questions, which is question 2 and question 3 from your experiment 4 worksheet. So firstly, we'll open up this program here called Olympus Stream Basic. Then we'll move on to the opening of the file. So we'll go to File, File, Open, Image. Once you're here, you select Perlite Ferrite 2. This is with reference to your question 2. So we're trying to find the percentage perlite. So essentially, why we're using this image is because this is something to do with consistency. In actual fact, we'll be using. You guys are supposed to use the steel pieces, the steel samples that you guys have done using the etching. But in this case, we do it something fast and simple. So we'll be using this. So once you load up the image in your Stream Basic, you need to calibrate the image. So we'll click on Image here. Scroll down and you'll find Calibrate Image. Click on it. So then you set reference distance. And from here, you use your mouse. You just click anywhere on the screen. Move to about 50 pixel. Click on it. It doesn't have to be exact, but 50 pixels roughly where you want it to be. So you mouse 1 again, then right click, confirm input. Then you just make sure there's distance 50 to millimeter. Then press OK. So once you're done, press OK again. So the image is done calibrating. So from here, we'll click on Phase Analysis. Then we'll click on Next until you find ROI, which is which basically means region of interest. So let's say I want to look at this area here. So I'll just mouse 1, then move my mouse and click again. So this is the box that I'll be focusing on. Okay, then click Next again. This is on threshold. So essentially, the red color is called perlite because of the columnar grains, while the white color portions are, or the green portions, the green portions are ferrite. So under the phase name itself, we're going to rename them. So the red one is perlite, the green one is ferrite. Okay, so we're done here. We'll now click Next again. So object filter, so this is the area that we're focusing on, and press Next again to get the result. So as you can see here, perlite fraction is about 52.99%, but it should change depending on which area you choose, but roughly is around 50%, 60%. So yeah, just press Next again, should give the same thing. So that's it. So for your question 2, your percentage perlite should be 52.99%, or 53 also works. Then for the same question, they also asked about the percentage carbon within this 52.99% perlite. So a rule that we all know is that for 100% perlite, there is approximately 0.83% carbon. So you guys will have to go and calculate yourself, but hinting, you guys should just you can just write it down 100 to 0.83, then you can just calculate from there. Okay, so now we'll move on to question 3, which is the grain size. So I'm just going to cancel phase analysis since we're done here. Same thing, file, open, image, and this time we'll use grains 2. So double click, it's going to load. As you can see the green circle and the red circle. So this image has already been auto calibrated, so you don't have to calibrate this time. Immediately just select grains intercept, then we just press next, next, next until we get image results. Then you can either use this answer or move on again, but the final answer is under results, which your grain size number is approximately 9.51. So for most low carbon steel, your grain size should be between 7 to 11, so 9.51 is right in between. So yeah, so that's it. Okay, then let's move on to your question 6, or your safety precautions. So essentially this question, I mentioned a few previously. One of them is using safety tongs to hold the specimen or sample during chemical etching. Then the other one, which is very common, is wearing long pants and covered shoes. Then another one why we use is the fume hood. So you have to perform chemical etching in the fume cabinet or hood. Then the next one is you gotta wear chemical resistant gloves during chemical etching of the sample or specimen. And lastly, when the test piece or specimen is dropped below the grinding or polishing area, you have to switch off the machine and wait for the wheel to stop rotating before picking it up. Yeah. Then the next question, they'll ask you for your quality of service on that. So this one will be given in an image during your experiment, but we won't be showing it now. Essentially, instead I will give you the answers, so you can just check it for yourself. So these are the 5 safety precautionary measures. Then this is the environmental policy. Yeah. So give you a few seconds to screenshot and write down whatever you want, or pause. Yeah. Okay, so then we'll move on to the previous few questions. So question 4. In cutting and subsequent grinding of a metallographic specimen, care is exercised so that the specimen does not become overheated. You have to state one reason why overheating a specimen is to be avoided. So this one, let's give you guys some time to think. The hint is overheating and in its surface or structure. Yeah. Okay, so essentially it's because when you overheat a specimen, it will cause some microstructural changes. So the main reason is that you want to avoid the change in grain structure. Yeah. Then your question 5, they ask for 2 advantages of the replica technique over conventional metallography. So what is conventional metallography? So conventional metallography is destructive testing in a sense, because you're removing a piece of the original material for testing. While for replica technique, you're not touching or you're not taking anything from the original piece, but instead you make something similar with while understanding the original material, so you can test it by itself. Hence the name replica. So that's one of your things. So one of the advantages is that replica technique is a non-destructive testing technique. Yeah. Then another thing is that replica is able to do on curved surfaces. Yeah. So replica is able to do on convex and concave surfaces. So here's the answers. So it's to prevent change in microstructure. Then replica technique is NDT, or non-destructive testing. Then it's also able to use on convex and concave surfaces. Yep. The last question, I'll just show you the answer. So this drawing is important. So the outsides, which is the closest to the surface, it should be chill, because the first one is to be cool when you're using when you cool a surface. Then the middle portion should be your equiaxed, and the second one in the middle should be your columnar. That's it. So as you can see, the numbers will definitely differ. So this one no need to worry. So roughly your percentage carbon should be about 0.5, 0.4, around there, 0.6, yeah. Just want to check, make sure you get it correct. Then your question 3 should be between 7 to 11. In this case, we got 9.51. So that's it.